Good afternoon, everyone. I hope you guys had a good lunch. I'm Ankit Papneja. I'm a PhD student at the Australian National University. I'm working with Professor Ben Buckler and Dr. Morgan Hedges on a new co-magnetometer scheme that we call non-equilibrium co-magnetometers or NECOMs. So let's have an overview of magnetometers or spin-based devices. So a single spin magnetometer, or normally called a magnetometer, are great detectors for magnetic fields as well as rotations, but they can give us only one measurement. So the thing is, they cannot separate between rotation or a magnetic field. Then we have an alkali noble gas co-magnetometers, which can provide us both the information, but they will have to suppress one of the information. They can differentiate between them, but will suppress one bit of information. Then we have something called an NMR co-magnetometers, which is basically two noble gases in our cell. NMRs are good at rotation sensing as well as magnetic field sensing. They can give us both the information on one axis together, but they cannot be operated in the SERF regime, because of which we leave some sensitivity on the table. So our idea is, how can we build a system which can give us good sensitivity, give us rotation and magnetic field information together? So let's discuss about the applications of spin-based sensors. So spin-based sensors have been used for a multitude of applications in the last few decades. So starting from study of fundamental sciences, which is something that we are mainly interested in. So we are a group of people who study dark matter, and we try to study the asymmetries and fundamental symmetries of the universe, for which we need information of magnetic field and rotation, which we will discuss later. For medical imaging, which we have been discussing in a lot of presentations since morning, MEG, which uses magnetometers for brain wave detection. For space exploration, we use magnetometers, spin-based magnetometers, to detect the magnetic field of extraterrestrial objects. And then we have navigation purposes, for which we use magnetometers or co-magnetometers as gyroscopes. So let's talk about the SERF alkali magnetometers. SERF alkali magnetometers are very highly sensitive. They have a lot of applications. They work in a cryogen free regime, so we don't have to worry about having a big chamber, as we have discussed in the previous presentations. And because we are pumping our alkali using a laser, we have minimal interference because of any electronic devices that we might need. But like I've mentioned before, these cannot give us the difference between a rotation and a magnetic field sense. Then we have an alkali noble gas co-magnetometers. So let's see how an alkali noble gas co-magnetometer actually works. So let's say we have our alkali cell, and then we add a noble gas in it. So if we add a noble gas, since the noble gas has a totally different, a very small gyromagnetic ratio as compared to an alkali, it will respond totally differently to any magnetic field that we are applying. So how do we get this? So we have now, as I've mentioned, we have two species in our cell. We optically pump our alkali, we polarize them, and through spin collisions, these alkali then polarize our noble gas, and then we have two different entities within one cell which can give us measurements. But alkali noble gas co-magnetometers, we have two different species within a cell which are polarized now. So they will start to precess around each other. And if there is an external perturbation, they will start to precess around that. And the dynamics of the system gets a bit hard and a bit complicated to study. So what we do is we apply a bias field on our system to push our system in something called as a self-compensation point. So let's see, what is the self-compensation point and why do we need the self-compensation point anyway? So a self-compensation point is when we apply the bias field, which cancels out the magnetization of our noble gas and our alkali too, both of them. So at this point, we can assume our alkali to be working in a net zero field. So what happens if we are at a net zero field? Any external perturbation that is applied on the system will give us big signals. That means we have a better sensitivity to any external signal any perturbation signal that we are applying. Secondly, if there is any small change in external magnetic field that we are applying onto our system, our noble gas will actually adiabatically compensate for it, or in other terms, it will suppress any external magnetic field, and we can have the information of rotation from that. So an alkali SERF co-magnetometer, alkali noble gas SERF co-magnetometer will actually, at a compensation point, will give us good sensitivity for both rotations as well as magnetic fields. But like I said, these cannot give us both at the same time. They suppress one information to give us the other. Then we have something called a noble gas co-magnetometers, or NMR co-magnetometers. So now let's put another species of noble gas into our cell. So now we have two noble gas species and we still have our alkali. It works the same way. We optically pump our alkali. Our alkali through spin exchange collisions will further polarize or pump our noble gases. But since both the noble gases have different gyromagnetic ratios, they will have different precisions to any external field that we are applying onto our system. And using the difference between these two, we can actually measure the magnetic fields and rotations that our system is about to sense. These are awesome magnetic field and rotation field sensors again. But like I said, they cannot give us information of both the axes. They can give us information of magnetic field and rotation together, but not on both the axes. They can give us one axis information. Also, like I mentioned, they do not work in the SERF regime. So we leave some sensitivity on the table. So the big question is, how do we get the best out of both worlds? So we get it by the NECOM scheme, or the non-equilibrium co-magnetometer scheme, which I'm about to discuss, which is our noble scheme. So let's try to understand the scheme. So in the previous alkali noble gas co-magnetometers, we discussed that we are continuously pumping our alkalis. But instead of doing that, now let's just pump our alkalis with pulses. We use high power pulses to actually pump our alkali. What these pulses will do is they will kick our alkali and they will just push them into one Z direction, the direction of direction that they are being pumped in. We push our alkali in those directions. We have an oscillation. Alkali start to precess and then decay. And right when they decay, we give another pulse and our alkali start precessing again. So by doing this, we actually get the information on both the axes. Let's say we apply a BX field and a BY field, we get different signatures for both of them because of these pulses. Next, we apply magnetic field pulses onto our system. So what these magnetic field pulses actually do is, since our alkali is already getting polarized or pumped in one direction, these magnetic field pulses will not affect our alkali. These magnetic field pulses will just act on our noble gas, pushing it in one direction with one pulse. And since we are using alternating pulses, the next pulse will push our noble gas into the other direction. So doing this will actually give us the ability to extract both the information for rotation and magnetic field together in the same measurement that we will discuss later. So to study any coupled system, we need to solve what we call coupled block equations. So we see there are three types of terms in the coupled block equations. One is the capital B, or the magnetic field terms. Another one is the omega terms, or the rotation terms. And then we have the small b, or the dark matter detection terms. We will keep the dark matter detection terms for later. Let's just talk about the magnetic field terms and the rotation terms. So here we see that we have something called a Bn effective and a Be effective, which is the effective magnetic field of the noble gas and the alkali. Remember, we are working in something called a self-compensation point. So we are compensating for these two with our self-compensation point using a bias field. So when we use these equations to actually simulate our system, we don't need them. So we actually tried to simulate our system and we came up with some really, really interesting results. So let's get our laser safety goggles on and let's try to see what our pump is seeing right now. So let's zoom in on the, why is it pixelated? Okay, let's just try to study what is actually happening in here. And this is really interesting, trust me. So first we apply this pulse, a pump pulse. What the pump pulse will do is it will send our, and there is an external perturbation be in the magnetic field perturbation in the x direction. So a pump pulse will actually make our alkali go like this. And simultaneously we are applying a magnetic field pulse. So since our alkali is already pumped in one direction, the magnetic field will not affect it, like I mentioned before. It will just affect our noble gas spins. So our noble gas will just come from here to here. So when we are applying such a system. And next, we apply another pump pulse along with another magnetic field pulse, but in the opposite direction. From here to our noble gas from this position to this orientation and make our alkali go in the other direction. So what we see here is another interesting thing is for all the types of perturbation in all the directions, we get totally different looking curves here. So if we see the projection of these curves on our x-axis, which is the direction we are probing in, we can find 4 different traces of all the 4 perturbations that we can apply onto our system. This is really interesting. It means that we can measure, using our system, we can measure any 4 of them, so totally different and independent of each other. Also, another important thing to mention here is that each pulse cycle comprises of 2 pulses, and each pulse cycle is 1 data point when we actually try to map our data, to map this to our actual data. Another interesting thing that our simulations gave us were these results of sensitivity. So what we say here is, for the rotation sensitivity, we see that we have almost the same, maybe a slightly more sensitivity towards rotation as compared to a CW magnetometer that we have already discussed. And for magnetic field sensitivity, we see that this curve here shows that we can actually measure both of them, both of the directions, Bx and By. We lose some sensitivity when we compare it to a SERF magnetometer, but we can still gain information on both the axes, which we actually wanted. So we ran our experiments and got some really good looking results. Morgan smiling. So first we apply a slow varying field. So a slow varying field, or you can consider it as a DC field. So we all know if there's a DC field, our noble gas as well as our alkali will respond to it and we will get some signatures. Nothing interesting there. But what happens when we apply a sudden field or when we apply a fast varying field? So when we apply a fast varying field, we see different signatures, because now the fast varying field will not act on our noble gas because of the very low gyromagnetic ratio of the noble gas. It will not respond to a fast varying field, but the alkali will. So we will get different traces for a fast field and a slow field. But the important question is, why do we care? Why do we care what happens when we apply a slow field or when we apply a fast field? And the solution is because we can actually decompose our fast field into 2 fields that are acting on our noble gas. So we can think of it as a slow varying field pushing our noble gas into one direction, and an equal and opposite rotation pushing our noble gas into the other direction or in the opposite direction. So the net resultant of them is actually 0. So it means our noble gas is not moving. This is a very interesting way of measuring things or thinking things, because we can actually use this. So this is the total data that we are getting now. But this is not what we want. We want information of rotation and we want information of magnetic field. We have the information of a slow varying magnetic field from our slow magnetic responses. So what we do is we use these 2 plots, and the fact that we can decompose our fast magnetic field response into something of a rotation and something of a magnetic field, we get these interesting looking curves. We have some response to a magnetic field, and we have some proxy to a rotation that we can apply on the system in the beta signatures. So now, since we have our curves, or since we have our signatures, which, like I mentioned, we will be using there are 2 pulses in there, and we use this as 1 data point. We can actually use this to measure things in our system. So what happens when we apply a magnetic field? So we try to apply a magnetic field in Bx and By direction. And as we can see here in the first plot, that our system is able to, with some good accuracy, we can measure them. We can see what fields we are applying. That's not the interesting bit. The interesting bit here is the second plot that we see for beta. Since we are applying a magnetic field pulses, we should not be getting any rotation. And if you see this plot, the average on the rotation or the beta is 0. So means on an average, we are getting no response. There are some spikes, but that's because there's a sudden change. And as soon as that happens, instantly it dies out. and we get zero field again. Next, we apply rotational modulation. So this is interesting because we just shake our table for this. At 100 microhertz, we just shake our table in a magnetic noisy background. So we see here that since we are applying Y rotational modulation in our system, we are able to sense something in this red plot, which is our magnetic, which is our rotation. And we see there's on the x-axis, we don't have a lot of measurement. Means we are measuring the axis that we are applying a modulation to, we are able to measure it perfectly. But here also, the interesting result is the first one. You see this noise that we are measuring here is actually the background noise. And if we see the amplitude of this, we see that the magnetic noise is not actually affecting our rotation measurement. So it means that we have a good separation of, when we are measuring magnetic fields, we have a good separation to rotation, and we are measuring rotation, we have a good separation to magnetic fields. That we can see here. So if we are applying a BX field and we start our measurement, it instantly kills all the other rotation measurements, and we can have a very high separation. And same with the Y. If we apply a Y modulation, we can kill the rotations in Y very fast. So in conclusion, the theoretical sensitivities of our scheme are similar to the state of the art on all the 4 axes, and the crosstalk separation of our system is much better than the previous models. In future, we want to do some experimental demonstrations of how our relative sensitivity would work. This here was a proof of concept that we have built, but we want to build a better system, and so for that we are working right now. The story does not end here. As promised, here let's talk about the dark matter terms. So we see that one thing that we can see is the dark matter terms are a part of both magnetic field as well as rotation terms in our equations. So what this tells us is that if we are doing a magnetic field measurement and a rotation measurement in the presence of dark matter, by finding some ratio of that, we can actually detect dark matter using a model which can separate both of them. So what is dark matter? So about 85% of the universe is actually made of dark energy and dark matter, which we cannot see. They have very less interaction with the matter. But we have something called axion-like particle models. So along the information that we are getting from our system, along with the axion-like particle models, we can actually detect dark matter using our system. I'm not saying we have detected, don't get me wrong, but this is a good thing that we can do, and we are excited to do. We are a part of a global collaboration known as GNOME. We're the only group in Australia that is working with GNOME currently. It's the global network of optical magnetometers in search of exotic physics. So now the actual conclusion, I promise. So 2 new things that we have added to this is our system is a good candidate since we can separate the rotations and magnetic fields. Our system is a good candidate for dark matter detection experiments, along with our future prospect that we are trying to push a more refined data for the GNOME collaboration, and hopefully someday we will be able to get some good results with that. Thank you. Any questions? Yes.
How is it that you do the rotation modulation?
Yeah, we just shake our table.
You just shake the table.
Yes, that's a rotation in a very interesting way. Yeah. Yes.
Curious, at the start you mentioned you had a bias field you applied to the system and a self-compensation point.
Yes.
How do you sort of calculate or find or calibrate that bias field?
So